Oh, we did.
Okay, guys, I sent out a survey 2. So can you please do me a favor to fill this as provide some feedback? Guys, I'm asking.
Is it on Canvas? Or is it an email?
I sent you a link on Canvas. Several days ago. Several days ago. Okay, for the homework 4, we have finished the problem 3.5. I hope you guys have already almost finished all these things. Because I give you the detailed derivation. Today we are going to move on to next problem. So next problem is this. So derive expression for the J integral in a deeply notched 3-point band specimen. So this is some tables for this is a problem. This is 13.2, okay? In terms of the area and the load crack mouth opening displacement curve, begin with the corresponding formula for the P delta curve and assume a rotation about a plastic hinge. And it is the plastic hinge. The specimen with unit the thickness. So what it says about this? Right? So this is a P and delta P, and P is the applied load, and we can measure this applied load, and delta P is the distance at this the point which we applied our load on. So we want to do this. This is a specimen. This is a specimen, and we work. This is a specimen. So for this specimen, and how can we get this? We start with this equation, right? So this is equation, and so we start with this equation for here. And in order to do this equation and to integrate this equation, we need to know the delta P. And how can we get delta P, guys? Delta P, we need to use the similarity of the problem, and we still come back to this one. So this is, I told you guys, this triangle. So this is triangle, and this triangle is the two right triangles, and they are the same. So this is, the second triangle is here. Okay, if I draw a line here, it goes through this point. So this line, this is the right triangle. So this right triangle and this right triangle, they are the same. Why they are the same? Because they are right angle, right? And then, so this angle, half of this angle equals this. So as a result, we can use the similarity, or we can use the similarity between two triangles, and we can have. So this is delta P, right? So this is delta P. This is our delta P, and so this one. So from here to here is 2W. So this is hypotenuse of this right triangle is 2W. So delta P over 2W and equals half of this VP over and this guy's hypotenuse. So this guy's hypotenuse equals so this is half of VP and divided by half. Right? Why is it half? Because so this one we just use the vertical line and to divide this area on the equally. So here vertical line. So this half of VP and it divided by and this guy's hypotenuse. So this guy's hypotenuse equals an A and plus RP multiplied by W minus A. And W minus A and it is the B. Right? So this is the is a B. So this is A plus RP multiplied by B. RP multiplied by B. On B equals W minus A. Right? So this is B equals W minus A. So based on this is the equation, and we can get based on this equation, we can get this delta P and equals 2W multiplied by VP divided by A plus, and this is RP multiplied by B. Any questions for this equation? No question, right? No question. Then we can say, suppose this A is a crag, and we just say if the crag does not change, and assume A remains the same. A does not change, and then we take a derivative of these two sides, and then we can get so this equation D and delta P equals 2W I'm sorry, so here is no 2 here. So here is W A plus RP multiplied B, then multiplied by B VP. So we assume W, A, RB, RPB, and all of these guys are constant. So the increment of delta P will be equal to the increment of delta D VP and multiplied by this factor. Questions so far? No question, and then we come back to that equation, and then we start with so this equation, right? So we focus on the plasticity part. We can see we assume a rotation about a plastic range. So this part, first part, can be neglected, and so we will have this J and equals and this Ki square divided by E prime and plus second part. On second part we have 2B here and 2B, and then we have this from 0 to delta P, and from 0 to delta P, right? And so P is here. So D delta P equals this, and we just plug in D delta P multiplied by W and A plus RPB, and then D VP. Now here, so this is the upper limit, and we will change to VP. And so we can just rearrange this equation, and we can have Ki squared and divided by E prime, and then we just multiply. So this is constant. We can just the P is not constant. This is a constant. We can just pull it out. We can have 2W E coming inside. Okay, so this is A multiplied B and plus RP B squared. And then we have this integration sign. So VP and P and D VP. So finally we got this one. And we also know that assumption is about plastic range. Plastic range means that so this one can be neglected, but to be complete, I just wrote here. No, so this is it's okay. You can just carry this one. Any questions regarding this? Yes, guys? No question? No question, we look at the 3.7. 3.7, we need to look at the figure. I'm going to show you guys, okay? So on 3.7, it says that a weather plate with a through thickness crack fills at 30% of the yield strength. To estimate the elevation in Taiwanese J critical over J zero resulting from constraint loss. We have assumed N equals 10, and the JQ locus for this material is given by this one. I'm going to show the figure, no worries. And the by accidentality ratio B equals 0 for this geometry. And what do you think? What do your results say about the validity of single parameter fracture mechanics for this geometry? So let me take a photo of what I just wrote before I erase them. For this one, 3.7. So we can recall that if you have the lecture 16 and we talk about the small scale yielding, right? We talk about the small scale yielding and small scale yielding. And the small scale yielding, then we can just use one single this is parameter to characterize. And if it's a small scale yielding, we can use a single parameter. And we can use single parameter. And we use single parameter. And to characterize the crack tip. Crack tip field. So this field can be the stress, strain, and displacement. And however, for this larger scale yielding, so this is large and scale yielding. And so we have LSY. For S small scale yielding, we have SSY. And the larger scale yielding, and large and small means the plastic zone. If the plastic zone. If the plastic zone. For larger scale yielding, then we have three options to solve the problem and to characterize the two parameter, right? So we have two parameter models. And so what we have learned, this is a T and KT model. And we have learned, well, this is a two parameter models. And first one is a K and a T. We still have stress intensity, and then we also have is a stress T. Is our first one. And second one, we talk about the J and Q and JQ. So this is two parameter the model. Now for this problem, so you can see the crack, the crack thickness, the fills is the filling, the yield strength. Okay, the yield strength, the filling critic, this is the, let me show you the figure. The Q and T, and this T is stress, this T is stress, and you apply, and this T is stress, you apply. This T and here, okay, so here, this is, we know that based on this problem statement, and we know that the wet plate with the through thickness crack and fills at 30% of yield strength, and 30% of the yield strength. So this is talk about T, right? That means T and divided by sigma equals excuse me, and this T divided by sigma equals the 30%. However, and here is the two directions. One is negative, one is positive. And because T is lower, okay, and T is lower, and then yet on this figure, and we go in this direction. So this is that means so this is negative. So T divided by sigma is negative 0.3%. 3%. This equals negative 0.3. For this figure, if we have T sigma, so this is negative 0.5, 0.1, 2, 3, okay? We draw a vertical line, and this vertical line will intersect with this is you can see here n equals this line is equals 10. For n equals 10 here, right? So this curve, 1, 2, 3, the third curve, and we will draw a line here. So this line intersects at this point. So this point is point 1, 2, 3. Go. So this is point 5, and this is equals 0.275. Okay, so this is Q, and from figure 3.7, 3.35, and based on this one, and also n equals 10, and we can get the Q and equals negative 0.275, and you just draw a vertical line. Then you get this value. This is Q equals 0.275, and then we look at the JQ. The JQ the curve. JQ curve is this one. This is a J. This is a you have Q. Okay, Q. This is Q, and Q for our case it equals negative 0.275 or the 3 here. This is about here. The gamma equals 1. The gamma equals 1 here, and you just draw a line. Right? It is intersects with this gamma equals 1. Here is about 1.8. So this is 1.8 here. That means J critical over J0, and it is 1.5. And so based on Q, right? Using Q equals negative 0.275, and then checking and figure and 3.39, and then we can get and J critic divided by J0 equals 1.8. So this 1.8, it means that so this is a critical. That means the corresponding critical value is elevated by the factor of 1.8, okay, so that means, so this is J critical is elevated by that means, so this is elevated by 80%. So as a result, so this is for this is problem. So one single one single parameter assumption is doubtful because this is 1.5 almost 2. So single parameter assumption is not right. It's doubtful. So what circumstances should we do this? Before we do anything, okay? Because we do not suppose this is a new material. Because we use new material and we do some experiments, and at the very beginning we assume this is a small scale union, right? Because it's totally new for us. We have no idea. And then we can just use this one to check if this is the single parameter assumption is good or not. And how to do that? And first, you will test under what condition. So this guy fails, okay? Is it correct? And what condition it fails? And then this T, it's get a ratio of T to this is a sigma 0. So this is the yield strength. So this is the yield strength. Right? So sigma 0 is yield strength. After you get this value, and then you just check this n number. N is the hardening material, a hardening parameter. And then you check this figure, and to get the Q, after you get the Q, go to the figure 3439 and to get the ratio between J critical to J0. If these two values are very, very close, it means that a single parameter assumption is okay. But, so these two guys, this is almost double. That means it's not okay. As I said, at the very beginning, for new material, we have no knowledge, no idea about how this guy works. Then we just make some assumption. This assumption is, we suppose we can just use the parameter, the model, for example, using G, to characterize the corrective solution field. But finally, when we see this one, and we know that the single parameter assumption is not right. What? So as I said, some people might say, maybe you already know this one is single parameter assumption is not right. I'm just as I said, okay, at the very beginning, when we do anything on this new material, you have no knowledge, right? If you have knowledge, that means you do not need to do anything about it. Do you guys agree? Before we do anything for these new things, what should we do, guys? We make some assumptions, right? That is always we do when we approach the new items, new ideas, new things. We make some assumptions. If finally it works, that means our assumption is okay. However, if the results are contradictory to the facts of literature review, literature results, or our own results, that means our assumptions are not good. You guys agree? So this is how I approach new things. Right? To simplify the problem, I need to make some assumptions. Then I will check. And the results are realistic. And then if the results are realistic, I think my assumption is not right, it's not wrong. However, if my results are not realistic, I will say my assumption is not right, and then I need to change my assumption. So this is just to tell you, whenever you approach a new problem, new material, and you do some tests and calculate the T, then compare the ratio of the T to this is yield strength, right? And then if this one get, I will get this one, you get the Q, I will get the Q and go to, this is a figure 3.39, and to get the J critical ratio and to the J0. If these two guys are very close, that means your assumption is okay. That means single parameter J can be used to characterize the corrective solution field. Otherwise, that means single parameter model fails. Questions so far? So when can you give me the homework for? One can complete. Can you give me this Friday? Okay, give me Friday, okay? So I want you guys I'm almost give you all the steps, but for the some previous problems, and we covered in the previous time class sessions, and I just skip several the steps. I leave these intermediate steps for you guys. You need to complete, okay? And then you give me your results. I want you, when you finish this one, and I want you to use your hands and to draw something, to write something, and also use your minds to think on how we solve this problem. It's very theoretical. This course is very theoretical, but it's very useful. It's very, if you are going to go to the graduate school or to some national lab or industry, to do some mechanics related things. Okay, questions for me? No question. We still have some time, and I want to continue our talk about last time we talked about the KR curve, and today we are going to talk about the lecture 20. Yeah, I tried to print them out, but the printer in the dean's office does not work. I don't know why. So just before today's class, I went there, but it did not print out. And I will give you the handout Wednesday, okay? So we talked about lecture 25 last time, and today we're going to continue our talk about lecture 26. So these are very, very important topics, important skills, and you might find them useful when you do some experiments. So today we talk about G testing of the metals. Is a very, very important part. The current ASTM, I told you what is ASTM. A standard that covers J integral testing is E1820. Okay, so I want you guys to know that, and you can get this is a protocol we call protocol with standards or procedure or rules, and they are available online for free. And whenever you do some tests, and you need to search on what kind of ASTM protocol or protocols you can use. After that, and you need to download these protocols. When you do the experiments, you need to follow the protocols closely. Okay? As I said, why we call standards? If you do not follow the procedures, the standards, protocols closely, your results might not be able to be duplicated by other people, or and you cannot see your results how close your results are with the published results or the other people's results. So and you need to follow the procedure closely. So this standard is actually a generalized Clebner-Kovnes method, and it is also can be used for KIC and the stress intensity factor, critical, C critical, and also CTOD tests. So this has two alternative methods, and for this is the G test, method G test. The basic procedure. Second one is the resistance curve procedure. So the basic procedure entails monotonically loading the specimen and to failure or to a particular displacement and depending on material behavior. So this is a basic procedure. And second procedure, the resistance curve procedure, and then requires that the crack growth be monitored during the test. The J integral is calculated incrementally in the resistance curve procedure. The basic procedure can be used to measure J at fracture instability or near the onset of ductile crack extension. The latter Tauponese value is designated as the JIC, right? The JIC. So this is ASTM E13, and you can use calculate the JIC, and you can 1981 and 1987. These are two versions. And so ASTM E1152, you can just get the JR curve, and last time we talked about JR curve, and J is integral, J integral, R is the resistance curve, resistance, and these two guys, we put these two guys together, and we can know and what condition this crack will grow, and how it will grow, and how long after it grow it will stop. So this is 1987 is the version. So specimen. We have two specimens, and that's our commonly used one. And one is called, this is a compact, and one is called a single edge notch bending. This is a specimen. So JIC measurement, and you can use multiple specimen or single specimen. Okay, so multiple specimen, and you need to expend a lot of money on it. So this is the measurement. So measurement, and you can use the direct measurement or compliance measurement. So can somebody tell me what is a compliance measurement, right? What is a compliance measurement? Compliance measurement means that we just load, this is a specimen, and after it yields, and we load, and then sometimes we unload, okay? And then we go back loading and unloading, loading and unloading. And for each of these loading and unloading, you will find that the slope of this curve are changing. Why they are changing? Because the crack is growing. The longer the crack, the more compliant the material is. Do you guys agree? Right? So as a result, you will see the figure, the slopes will go this way. So this compliance. And so A is a function of C, and this is a polynomial in the C here. So this is compliance. C is a compliance. So this is AW, okay? So this is AW. A is a crack length. W is this is the width of the specimen. So they have this is a polynomial, and UL, okay? This is UL equals 1 over square root of ZLL plus 1. ZLL equals BE delta and P. And P is loading, delta is a displacement. And what is the E, guys, here? What's the E? What is the E here, George? Make a guess. Mechanics, right? These Young's modulus, right? This Young's modulus. Or what is the B, Maxim? B?
It's the thickness.
Yeah, thickness. And B is the thickness of specimen. Young is a material parameter. Young's modulus. Delta is the displacement, and P is the load, and you are applying. So the various J testing standards provides polynomial expression that relates AW. A is the crack length, W is the width. To compliance C, right? Compliance C. This is a table. lists this compliance equation for bent and compact specimen. The ASTM standard requires relatively deep crack, because the unloading compliance technique is less sensitive for A slash A over W when A over W is less than 0.5, and this is a compliance test technique is not sensitive. I'm going to stop here now, guys, and so this one I want you guys to pay more attention and to this one, because it is very, very important. It's very when you really want to do some experiments to determine something. ASTM, in my own opinion, and we should teach the ASTM and our students the ASTM, and we should have at least one example to illustrate whenever we are given a task, and how can we get the ASTM, and then which protocol we should use, and then how can we design, build, fabricate the specimen, and then we follow this procedure, the corresponding the right procedure, and to do the experiments. Otherwise, your results will not be convincing to other people. Okay, guys, I'm going to stop here now, and I hope you guys have a wonderful Monday. And also, you need to digest thoroughly on the derivations of all the problems for the homework. Okay? Make sense? So if you have any questions, if you are confused by any details, and you are welcome to see me. And also, last time I told you guys to come to see me during the office hour, or if you have time conflict with the office hour, you can just come by anytime whenever I'm in my office. And I want to talk to you guys. I want to know you guys better, how you are feeling about this class, and what your expectations are. How can I help you? If you don't have any questions, you can just sit there, say Dharma, and you have a lovely day. Okay? Okay, guys, without further ado, I'm going to end today's session, and I hope you have a wonderful Monday. Also, as I said, you need to understand all the derivations, all the steps in the homework 4 problems, and then give me a wonderful homework 4.